Okay, so started recording. Let's begin. So we are doing antennas and radiating systems. So we'll start with the radiating systems part kind of today. Where, so in the last class we were doing antenna arrays. We did linear antennas. Today we'll start with receiving antennas. So, sorry, module 6, and we'll cover internal impedance and directional pattern. So which is a very small section in module 6. And in the next class we'll cover effective area and backscatter cross section. And we're following DK Cheng, and this is module 6 in the textbook. And we'll be following the textbook today. I have been planning to give out an assignment. I've started making it. I see that in the group somebody had shared the solution to the this DK Cheng textbook. So I'll be giving out questions from the textbook itself. And since you guys have the solution, so if there is any confusion with the solution, we can discuss that. You can practice those questions on your own. This is just meant to be like to complete the like the complete for the completion of this course. But you need not return the assignments. If you have questions, we can discuss them. Okay. Previous class we covered general uniform arrays, and today we'll do internal impedance and directional pattern. So in transmit receive system, we have two antennas. One is when we have a wireless channel, we have two antennas. So the one is on the transmitter end and one is on the receiver end. So so far we were kind of discussing the antennas if they are in the transmitting mode. What happens if they are in the receiving mode? So in the transmitting mode, a voltage source is applied and to the input terminals of the antenna, which sets up currents and charges on the antenna structure. And this time varying currents and charges, they in turn radiate electromagnetic waves, which carry some kind of information that we intend to send. A transmitting antenna can be then regarded as a device that transforms energy from the source generator with the voltage source or the current source, which is feeding the antenna. Uh, and the antenna is the device which converts this energy from the source to the electromagnetic wave. So now a receiving antenna, on the other hand, extracts this energy from the incident electromagnetic waves. So let me kind of just draw an illustration. We have some kind of source over here, and then this source is connected to some antenna, and then it puts up some currents and voltages on this antenna, and then it forms currents, electric fields and magnetic fields, and then this radiates. So this is the transmitter. Now the receiving antenna, on the other hand, receives this electromagnetic waves because these electromagnetic waves induce some currents and voltages on this antenna, and then whatever the voltage is received is then transmitted to a load. Some load is attached to this antenna. So the receiving antenna, on the other hand, extracts energy from the incident electromagnetic wave and delivers it to the load. In the receiving mode, the external EM field that causes it causes currents and charges to flow is incident on the entire antenna structures and not on just the input terminals. So what this means is the you have some antenna, right? So this antenna is a pulsar. So even if you even if we intend that this waves are incident on some particular area of the antenna, it will irradiate the entire antenna structure, even the parts which are not intended to radiate or receive. So the entire structure is illuminated, and currents flow throughout currents and charges are developed throughout the antenna structures. Now, so this may create some problems. Now, what that means is the induced current in charges, which depends on and the other thing is, for example, if we intend the transmitter over here, it's it creates some EM waves, and then we have a receiver over here, and so it will be incident. So for this scenario, there will be some currents which are developed on this. There will be some currents which develop on the receiving antenna. But if this transmitter was at some other distance, or so this distance, let this be R1. So if this distance but changes, and the angle of reception as well. In this case, the currents developed, for example, I, let's just say this is I1, okay, for now. So this I1 will not be same, and in this particular case, when this distance is R2, and then we have some angle between these antennas, between the transmitter and the receiver system. In this case, this I2 will not be same as the I1, so they won't be the same. So in this case, so which depends on the direction of arrival of the incident EM wave, and also this will produce re-radiation and scattering of the electromagnetic energy. So whatever EM wave which is incident from from the transmitting antenna to the receiving antenna, a part of it will travel to the load, and rest of them and part of it will be it will travel to the load, or the antenna receives it and then re-radiates it, and some of it will be just reflected back, some of it will be back scattered. So some of it will be received by the load, some of it will be re-radiated, and some will be back scattered. So these three things can happen. So hence, this makes the calculation more complicated. But what we'll do is we'll see that the amount, if designed properly, or will also the re-radiation and backscatter is usually very minimal, and we'll try to solve for it. And at places, we'll just ignore them or approximate them in some ways. Okay, so that's what we'll do. So we may reasonably expect that the current and charge distributions on the receiving mode are different from those in transmitting mode. So if, let's say, if both these antennas were identical, so let's say both of them are some kind of horn antenna or a patch antenna. So if operated in the transmitting mode and when operated in the receiving mode, they won't have the exact same current distribution. So if it is transmitting, it will have it will have some different current distribution as compared to when it is in the receiving mode. But it will still be very similar. It will be different, but similar, not exact same. Nevertheless, despite these differences, reciprocity relations will enable us. So we have seen that we have been using this reciprocity relations. It follows when the media is we're considering all the measurements or the experiments or the en- environment. It is uh, we have reciprocal media around it, so we are doing it in air. So for example, which means that the channel is reciprocal. The way the waves travel in this direction is same as the same for the other direction as well. So one of the examples for a non-reciprocal media is ionosphere. Ionosphere is non-reciprocal. So if you want to know why and how, you can look it up. So it primarily has to do with the charged ions, and due to the charged ions, create some conditions with the permittivity. I think the permeability remains the same. Uh, the mu remains same, but the epsilon, yeah, the epsilon, sorry, the epsilon becomes function of space in this case, and due to space and time, maybe space and time. Uh, so you'll have yeah. So it's a discussion altogether on separate, but the epsilon becomes some function, and in that case, the media is not reciprocal. Anyways, back to what we were discussing. Um, so since the media is reciprocal and the system is reciprocal, this will help us conclude that the equivalent generator impedance of an antenna in the receiving mode. So we'll see that we'll have some equivalent circuit in which we have the antenna working in the receiving mode. We will have a load which is connected, and then the voltage which occurs between this load will have some generator impedance in the equivalent circuit for the receiving antenna, and this generator impedance will be equal to the input impedance of the antenna in the transmitting mode. So we'll see this. Okay, this may sound very complex, but we'll derive this now. And the directional pattern of an antenna for reception is identical with that of transmission. So we had seen uh, the radiation pattern in the previous classes. For let's say if there's a horn antenna like this, and its radiation pattern kind of looks like this with some small back lobe and some minor lobes. So for a receiving antenna as well, it will be same to some inner lobes, and okay. So they will be identical. The radiation pattern, the directional pattern, uh, in for the transmission and reception cases, they will be identical. Okay, so I'll pause over here and take any questions you have on the introduction to the receiving antennas. Okay, so I guess that was pretty straightforward. So and you got the time to go look at the slide. So we'll proceed. Yeah. So we'll justify the conclusions by using equivalent network representations. We'll see those in the next slide. So this is the equivalent circuit, and this is the scenario. We'll go through them. So let us assume there's a transmitter antenna A. So this is our transmitter, and it radiates some electromagnetic energy which is absorbed by a distance receiver B. So this is our receiver. And a receiver could be in two different positions. It could be here, it could be here, it could be anywhere here. So let's say we can move the receiver and we have the transmitter over here, and it is at a distance r. So it remains at a distance r, and we have this varying angle theta, and in this direction as well as phi. Okay. So we can vary this is its location and in the angular fashion use by varying the theta and phi. But if we keep it at a certain distance r. So antenna B moves about antenna A at a constant distance r and is always oriented in such a way to receive maximum power as illustrated. So so over here we're kind of considering an omnidirectional antennas to keep the calculations very simple. So it radiates equally in all directions, and the antenna B receives equally in all directions. Uh, let's say it's an isotropic pattern, and we're keeping it at a fixed distance, and so it receives maximum power. Um, in a way. Or let's just say if it is not isotropic, if it's some directional antenna, we're just tilting the antenna A and B, like we're always keeping them in such orientation or by and fixed distance, such that it receives maximum power. Uh, if Yeah, so it receives the maximum power. The two coupled antennas and the space between them can be represented as a two-port T network. Okay, so this is the network that we're talking about. We'll see how this comes up. So the terminal characteristics for A and B antennas are V1 and I1. So we have voltage, V1 voltage exciting the transmitting antenna, and I1 is the current in the transmitting antenna, and V2 and I2 are the currents and voltage which is developed on the receiving antenna. So current I1 is developed on the or current V2 is developed, so the amount of EM wave which is incident, it creates this voltage and this much amount of current through the antenna terminals. So this implies that voltage V1 is equals to Z11 is the input impedance. Z11 is the input impedance of the antenna, and I1 is the current in the antenna terminals due to the voltage. And Z12 is basically due to the mutual coupling. So some of the wave which is transmitted will be reflected back, re-radiated, and antenna 1, the transmitting antenna will itself receive that excitation, and then it will also develop some currents, and that due to those currents we will have some voltage. So V1 is essentially affected by the current in the antenna itself, and the current uh, due to the re-radiation of the receiving antenna. So this is the V1, and similarly V2. V2 is largely dependent on the radiation from the transmitting antenna, and Z21 is due to the mutual coupling. So this is Z2 is the impedance due to the mutual coupling, and I1 is the current in the transmitting antenna. So the current in this antenna, which is radiated and received by the uh, receiving antenna, it will induce some voltage, uh, and this is the voltage which is due to that. And this, and again, this particular antenna in itself will have some input impedance, or it will have some input impedance, and due to that, some of the current which was transmitted will be used up by that. So that so this second term Z22 is due to uh, receiving antenna's input impedance, or we'll see that how that is equal to that, and I2 is the current which is developed in the receiving antenna. And these impedance characteristics are when circuit impedance coefficients. So these are some coefficients that, and the kind. So we've seen Z12 or Z21 are the coefficients due to mutual coupling, and 11 and 22 are due to the input impedance of Px and Rx. Okay, So I'll pause over here, let you to read the slides, and if answer any questions if you have on this. Okay, so we'll continue then. In the medium in the transmission path between A antenna, A and B is bilateral. That's what we were discussing in the previous slides, such that the reciprocity relations hold. The transfer or the coupling impedances Z1 and Z12 and Z21 are equal. So if the medium is reciprocal, so this medium has to be reciprocal. In that case, we have Z21 is equals to Z12. So the amount of mutual coupling which happens on A due to B and on B due to A, they will be same as long as the media is reciprocal or bilateral. And one of the examples that we know of non-reciprocal media would be ionosphere. Under normal circumstances, the transmitting and the receiving antennas are separated by very large distances. We have had some discussions on I think far field term, but which will I think discuss in next class also. I think next to next class. So we'll have more discussions on this. But in the usual scenario, the transmitter and receiver are at very far distances. Uh, for example, if you are communicating on a cell phone, so, and the waves which travels from your phone to the local tower, telephone tower or mobile phone tower, which is very far away or kilometers away, and then this travels to some satellite in space, which is again very far away, and then again to some tower, which may be to another tower, which may be to your the receiving device. So the usual scenario, all the antennas at each location are very far away. Even if you are, let's just say, if they're doing some indoors or local experiments, even in that case, the usual scenario is um, you have some remote control device and then you're communicating with some other device. So this distance is usually very far. Uh, yeah, and okay, so it is very far, and the coupling impedances are negligibly small. So the amount of coupling which is happening is very small. So as an example, the amount of power which we usually receive on our cell phones are in the order of minus 50 dBm to minus 70 dBm. That's the amount of power our cell phone antennas receive, which is very, very small. Uh, okay, so and the amount of transmitted is usually around 0 dBm to 10 dBm maybe. I think that's the maximum. Yeah, but do check. But yeah, so it's the difference is almost around 60 to 70 dBs around. Is the difference between the transmitted and the received signal strength. So, and the reaction on the transmitting antenna owing to the scattering by the receiving antenna is negligible. So, so for example, if you have some transmitting antenna, it is transmitting 0 dBm. And in the best case scenario, for example, your receiving antenna, let's say your Wi-Fi router is sending out 0 dBm, and your laptop over here is laptop is receiving minus 40 dBm, let's say. And then your laptop again radiates the power back to the transmitter of the Wi-Fi router. It will be around minus 80 dBm in the best case scenario, which is very less. This is very close to the noise floor, which will usually be around minus 100 or something. So the thermal noise and stuff. So this is very less. So this becomes negligible. So what in this case, so the amount of mutual coupling due to the receiving on the transmitting antenna due to the receiving antenna can be neglected. And in the case of limit this particular distance tending to infinite or like very large distances, the effect on one due to two is, tends to zero. So the parallel arm of the T network, this particular this arm can be considered short circuit. So if this becomes short circuit, we can separate this network and this network in two different circuits and then solve them individually. So I'll pause over here, let you read this, and if there are questions, you can ask. So if there are no follow-up questions on this, we'll proceed. Yeah. So uh, in this case, when this limit z1 to tends for large distances, this is 0. In this case, we can separate the this particular circuit into two circuits, and we have uh, yeah, for figure A for the transmitting end, we are using KVL and KCL. We have yeah, using the KVL, we have V1 is equals to uh, I1 into Z11, and since this is equals to I1, this is, and yeah, so this I1 is into Z11, and which is equal to the ZA into I1, which is where ZA was the input impedance. So we have shown that this Z11 coefficient is essentially the input impedance of the transmitting antenna, as we have negligible effect of Z12, and uh, and the equivalent circuit for this particular half is drawn here. Now, similarly, the coupling from the transmitting antenna to the receiving antenna, cannot, in this case, it cannot be neglected, since all the excitation which is happening in the receiving antenna. So this is for the receiver circuit, and this is for the transmitter circuit. In the transmitter circuit, we have ignored the effect of Z12, but in the case of receiver, we cannot ignore completely ignore this thing. So if, because if we ignore this, so over here also we had ignored the Z12 term, but over here we cannot ignore the Z12 term. So we take this entire term and call it some generator impedance ZG, and we cannot ignore it over here, because all the energy which is like circulating in this particular circuit is due to the uh, mutual coupling between these two antennas. If there was no mutual coupling on the receiver due to the transmitter, we would have zero voltage or current flowing through the antenna. So we cannot ignore that. So in this case, Z12 remains, but but it is but the effect in the short circuit are will ignore that. And in place of that, we will put some uh, voltage uh, which is due to the incidence. So this is the open circuit voltage which happens over here, which in this arm. So we have replaced this Z12 by some open circuit voltage, and this voltage is very small, but it's what drives this particular circuit. So we cannot just make it completely zero. But compared to the in the transmitter case, where we have V1, which is significantly larger than this particular voltage, which is over here. So we'll ignore that. Okay. So it cannot be neglected, since it is through this coupling that the latter extracts energy from the EM wave originated from the former. Former is the transmitter. So by using the Thevenin's theorem, it can be applied to the left of the load, and the load impedance ZL in the network figure 1117 over here, and to determine the open circuit voltage VOC and impedance ZG. So and the yeah, we're making this OC, and we're making this ZG, and where we achieve this particular circuit, and then by doing some tricks and maths, we will achieve these two expressions over here. So the first one is VOC is equals to Z1 Z12 upon Z11 to V1. So yeah, so to calculate this, if we are replacing the voltage in this terminal, let me just okay, let's just discard this and start the presentation again. Um, okay, so now the amount of voltage over here is VOC, right? This is VOC. So the voltage across this terminal would be, this is Z12, and this Z12 is much smaller than Z11. So we'll consider it to be Z11. And if we use KVL over here, so in that case, this VOC would become, Z12 is the amount, the impedance through this, by Z11 into this source voltage V1. Yes. So this is what we have gotten over here. So this is the open circuit voltage VOC. And for ZG, similarly for ZG, what will it will require a little more mathematics than this. So let me just how do I remove all the, how do I clear the slide? Or maybe just put this exit discard and just enter it. Okay. Yeah. And for ZG, let's try to calculate ZG as well. Now, from here we can see we have VOC. Okay, so this V2 is the excitation over here, and yeah, so V2 excites basically kind of reverse charges VOC, and we have some potential drop ZG over here. So VOC plus I2 into ZG is equals to V2. Okay. Now this implies ZG is equals to V2 minus VOC by I2. Okay. And this implies V2 by I2 minus VOC by I2. Okay. So and then we can simplify VO2, sorry, VOC, and we'll substitute VOC from here. So this will become V2 by I2 minus Z12 by Z11 into V1 by I2. I2, yeah, yeah. And now we have V2 by I2 as V2 by I2 is if we neglect this thing over here, it's approximately Z22 minus Z12 and we have Z12 by Z11 and V1 by I2 . Okay. So if so V1 by I2 will approximate will come around to be, do check this math once we're skipping some steps over here. So this will come around to be Z11 minus Z12. Yeah, let's check this. I'm not sure if I did all these steps correctly, but yeah, we'll end up with something which looks like this expression over here. And then in this case, since if we simplify this, we'll end up with Z22 minus Z12 square by Z11. And this Z12 is, since this is very small as compared to Z11 or Z22, and then the small, so this fraction is smaller. This particular fraction is much smaller than z22, and then again this fraction is again squared, so this is very small. And so in this case we can ignore this, which implies this zg is equals to z22. To solve for this expression in your time, but anyways we'll achieve this expression, and this implies, and this particular fraction is very small, which implies this zg, the generator impedance, is equal to Z22, and this is essentially the input impedance of the receiving antenna. So we found out that Z11 is equal to ZA, and Z22 is equal to ZB. So take a I'll pause over here. I'll let you go through the slide and maybe try to figure out this expression. If there are any questions, post them in the messages. I'll be away from the screen for a couple of minutes. When I'm back, you can ask me directly. Okay, so any questions on this? Or we'll just move forward. So I think something which I did not clearly explain over here was the steps to get this expression, but I think I trust you guys with the math. So if you do everything correctly, as opposed to me, but I did over here, you'll get these expressions right away. And so it is important just to note what approximations that we are doing instead of being stuck with the math thing. So we have to remember that we came up with this equivalent circuit, and then we assume that this is very small for the transmitting case. So the transmitting circuit looks like this, and this is and so we neglected this part as well. But in the case of receiver, we did not neglect it because this is the only source of voltage in our circuit, and we rather replaced it by some open source circuit voltage, and then replace this impedance by Zg, and then we solved it. So that's these are the steps that we must remember, and then these expressions is what we get. So to continue so we wrote down the voltage and current expressions. We used this particular limit, and then we found out that the Z11 is equals to the input impedance of our transmitting antenna A. We found out the amount of open circuit voltage which will be there on the term will be there in this receiving antenna, which is this ratio, and then we've calculated the generator impedance G, and since this Z12 term is very small, we can say that Zg is equals to Z22, and Z2, and this is equal to the input impedance for the receiving antenna B. So once we have this, now when the antenna B is receiving, we have V2, this the V2 voltage over here, which is equal to the current I2, which is flowing the opposite direction. So V2 is equals to minus I2 ZL. So this is the expression over here. So V2 is equals to minus I2 into ZL, and then we have the equation 1198, this expression, which can be rearranged. So we can substitute this V2 is equals to minus I2 into ZL over here. And then we rearranging it, we have eliminated V2 from here, and then we can calculate I2 in terms of I1. So we get I2 in terms of I1 like this. So this is the expression for current I2, and then we have the expression for voltage V2. So when if we know V2 and I2, um, so once we have I2 and once we have V2, we can calculate the time average power which is absorbed by ZL, and by using the pointing vector. So the power which is absorbed by ZL is equals to the real part of minus V2 and I2 conjugate. This comes from the pointing vector. Um, and then just multiplying these terms is something that we receive, like achieve over here. We have to note that we, since this ZL could be real or imaginary based on capacitive or inductive or resistive or a combination of these things. So we're keeping this real term over here. Okay, so this is the time average power which is absorbed by ZL. And if we change the position of this receiving antenna B from position 1 to position 2 in this case, this the term Z21 or Z12 will change because it depends on the orientation and the location. In that case, for different location, we can calculate the amount of power which is received by the receiving antenna, and this is the ratio for different theta and phi values. So we can calculate the ratio of the how much power is achieved at like received at what distance. So what we are trying to do over here is, for example, if we have the transmitter over here and we have the receiver over here, and if we keep moving the receiver, we can calculate the amount of power which is received at each distance. And once you do that, you can calculate the magnitude of the power around this transmitter, and you will, yeah, for example, if this is a horn antenna, you will probably get this kind of polar plot, and we achieve the radiation pattern. So this is what we were trying to do. So this is the directional pattern which we could achieve by, if we keep the transmitter fixed and we keep moving the receiving antenna through around it, we can get the directional pattern for the antenna, and find out in which direction the max radiation is maximum, which direction the radiation is minimum, where are the nulls, where are the side lobes. So this is what we were trying to do. So this is the by using this we can get the directional pattern. And just since the uh, and yeah, also the absorbed power, it is proportional to the square of the transfer impedance function, which is the Z21. We are calling it the transfer impedance coefficient. Yeah, so this is proportional to the square. And the other important thing, uh, so if in this case the transmitter and receiver were interchanged, but since the media is reciprocal, it follows that Z12 is equals to Z21, and in that case, the PL would, we would just replace that Z12 by Z21 by Z12, and again will be getting the same expressions. So that's for example, if we change the transmitter and receiver, um, the radiation pattern won't change, is what we're trying to say. So if they're interchanged, it really won't affect the direction pattern. Yeah, so that's about it. That's all we had to cover in this class. We'll be doing effective area and backscatter cross section in the next class. Um, uh, so I'll stop over here and take any questions that you might have from the last couple of slides that we did. So any questions on this? As I said, this was a shorter class. We'll cover the rest topics in the next class and take any questions that you have. I'll try to make up the assignment and share it with you guys. Um, yeah, I'll stop and stop for a few minutes and take questions. Okay, so if there are no questions right now, you can always email me or write in the group. So we'll end the class now, and okay, so stop the recording and yeah.